Start with the simplest possible question. Why is there something rather than nothing? Not how did the universe begin? That's a different question. One that cosmology has made significant progress on. But why is there anything at all? Why should there be a universe with laws and matter, and energy and stars and planets and consciousness, capable of asking this question? Why not simply nothing? This is not a naive question. It is, in the considered view of many philosophers and physicists, the deepest question that can be asked. And it has no answer. Physics can describe how the universe behaves once it exists. Mathematics can model its evolution from the first fractions of a second after the Big Bang forward. But why there is a universe to describe, why the laws of physics themselves exist, rather than nothing existing, not even laws. This question reaches beyond anything science currently has tools to address. Quantum physics offers a partial gesture toward an answer. Even empty space, it turns out, is not truly empty. The vacuum of space seethes with activity, particles flickering into existence and vanishing again so quickly they can barely be measured. A constant background hum of something emerging from apparent nothing. Some physicists suggest that the universe itself may have arisen this way, that absolute nothingness is somehow unstable, that something must always emerge. But this only pushes the question back. Where did the laws of quantum physics come from? Why should there be a vacuum with those particular properties rather than no vacuum at all? Others propose a multiverse, an endless ensemble of universes, each arising from quantum fluctuations, each with its own laws. In that picture, our universe is one bubble among countless others, and the question of why it exists dissolves into the question of why the multiverse exists, which is the same question, wearing different clothes. Philosophers have sometimes proposed that existence is simply the natural state, that non-existence is not actually a coherent possibility, that reality in some form must always be. But this is not a claim we can test. No telescope, no particle accelerator, no equation can tell us whether existence is necessary or contingent. Every other question in science rests on this foundation. Every star, every atom, every law of nature, all of it exists on ground we cannot explain, and perhaps cannot ever explain, which is, in its own strange way, rather beautiful. The universe didn't have to be here, and it is. We know the universe had a beginning, about 13.8 billion years ago. All of space, time, matter, and energy emerged from an extraordinarily hot and dense state. We call it the Big Bang, though the name is misleading. It wasn't an explosion in space, so much as the expansion of space itself, a rapid unfolding of everything from a state so compressed that our current physics cannot describe it. From that beginning, the universe cooled. Particles formed, then atoms, then clouds of hydrogen and helium that collapsed under gravity into the first stars. Those stars burned and exploded and seeded the cosmos with heavier elements. New stars formed with planets around them. On at least one of those planets, chemistry became biology. And billions of years later, here we are, asking about it. This is a remarkable story, and it is, in its broad outlines, well established by evidence. But what caused the Big Bang? This question is genuinely unanswered, and may be unanswerable in any conventional sense, because the Big Bang appears to be the origin not just of matter and energy, but of time itself. If time began at the Big Bang, then the question of what came before it may not be meaningful. Before implies a time before. And if there was no time before, there was no before. Some cosmological models suggest the universe arose from a quantum fluctuation in a pre-existing state. But this requires a pre-existing state with quantum laws, which raises the same question again. Others propose that our universe is one in a cycle of expansions and contractions, bouncing from a previous collapse. Still others imagine the Big Bang as a collision of higher dimensional membranes in a framework called string theory. None of these ideas has been confirmed by observation. The honest answer, the one every careful cosmologist will give you, is that we don't know what caused the Big Bang, and we may never know, because the event horizon of the Big Bang, the point beyond which light cannot reach us, seals off direct evidence of whatever came before. The universe had a beginning. The beginning itself is hidden. In the first tiny fraction of a second after the Big Bang, we're talking about a period of time so short it would take more digits to write it out than there are atoms in the observable universe. Something extraordinary happened. The universe expanded. Not at the rate it expands today, which is already remarkable, but at an incomprehensible speed, doubling in size over and over again in instants, growing from something smaller than a proton to something the size of a grapefruit in a period measured in billions of billions of billions of a second. This period is called inflation, and it explains several features of the universe that would otherwise be mysterious. Why the cosmos looks so similar in all directions. Why its overall geometry appears flat. Why the slight variations in density that seeded all the galaxies are patterned the way they are. The fingerprints of inflation are visible today in the cosmic microwave background, the faint afterglow of the early universe, a faint hiss of microwave radiation that fills all of space and carries within it the patterns of those first quantum fluctuations, stretched to cosmic scales by inflation's violence. But what triggered inflation? And what stopped it? We don't know. The leading idea involves a hypothetical field called the inflaton, an energy field that dominated space in that first moment, driving the expansion, and then decayed into the matter and radiation we see today. But no inflaton has been detected. No experiment has confirmed its existence. The model fits the data, but the physical reality behind it remains unknown. Something made the universe expand at unimaginable speed in its first moments. That expansion seeded everything that followed. Every galaxy, every star, every planet, every living thing. And we don't know what caused it. This is not a small gap in our knowledge. It is the gap between nothing and everything. Time flows forward. This seems so obvious it barely seems worth saying. The present becomes the past. Broken eggs don't reassemble. Heat flows from your coffee into the air, not the other way around. We remember yesterday and not tomorrow. The direction of time is so fundamental to our experience that it feels like a law of nature. It is, in a certain sense, but it's a strangely asymmetric one. Here is the strange part. The fundamental laws of physics, the equations that govern how particles move and interact, are almost entirely symmetric in time. Play a video of two particles colliding and bouncing apart, and you can't tell which direction time is running. The physics works equally well forward and backward. The equations don't care. And yet, at the scale of our experience, time has a direction. Disorder increases. Heat dissipates. Things age. Why should this be, if the underlying laws are symmetric? The answer most physicists give involves entropy. The universe began in an extraordinarily ordered state, low entropy in the technical language, and has been moving toward greater disorder ever since. The arrow of time is, in this view, the arrow of increasing entropy. Things happen in the direction that produces more disorder. But this only pushes the question back. Why did the universe begin in such a low entropy state? What set the initial conditions so precisely ordered that entropy could have a direction to increase in? We don't know. And here is the part that I find worth sitting with at this hour. You are living inside time's arrow. Every moment of your experience, every memory, every anticipation, every sense of the day having been, depends on this asymmetry that physics cannot fully explain. The fact that you can lie here, remembering your day, anticipating tomorrow, existing in a present that feels distinct from both past and future, all of this rests on a mystery that the smartest people who have ever thought about it have not resolved. Time is the medium of your entire life, and no one fully knows what it is. Now here is one of the strangest facts about the universe. Everything you have ever seen, every star, every galaxy, every atom in your body, and in every other body, and in every planet, and in all of everything. That is approximately 5% of what exists. The other 95% is invisible to us, not just hard to see, invisible in principle, unreachable by any light or electromagnetic signal or conventional instrument we have ever built or conceived. We call it dark matter and dark energy. Dark matter is the closer mystery. Astronomers first noticed it through its gravitational effects in the 1930s, when Swiss astronomer Fritz Zwicky observed that galaxies in the Coma cluster were moving far too fast to be held together by the visible matter they contained. Later observations of individual galaxies showed the same thing. Stars near the outer edges orbit at speeds that should fling them into space, and don't, held by something invisible. That something is dark matter. It is everywhere,
woven through galaxies like an invisible skeleton, clumping along the vast cosmic web of filaments that connects galaxy clusters across billions of light years. Without dark matter, galaxies would fly apart. The large-scale structure of the universe would not exist, and we have no idea what it is. The leading candidates are undiscovered particles, WIMPs, weakly interacting massive particles, or axions, or sterile neutrinos. Enormous experiments have been built to detect them. Tanks of ultra-pure liquid xenon buried a mile underground wait for a dark matter particle to collide with a single atom. So far, none have. Decades of searching have found nothing. Perhaps dark matter is made of something else entirely. Perhaps it is primordial black holes formed in the early universe. Perhaps it points to a modification of gravity itself. Perhaps it is something no one has yet imagined. Whatever it is, it outweighs ordinary matter 5 to 1. The universe is mostly something we cannot see. Dark energy is stranger still. In 1998, 2 teams of astronomers were studying distant supernovae, stellar explosions so bright they can be seen across billions of light years, and regular enough to serve as distance markers. They were expecting to measure the rate at which the universe's expansion was slowing down. Gravity, after all, should be pulling things back together. Instead, they found the opposite. The expansion of the universe is accelerating. Something is pushing space apart faster and faster, overcoming gravity on the largest scales. And it is not concentrated in galaxies or clusters. It is uniformly present throughout all of space, equally dense everywhere, in the vacuum itself. We call it dark energy.
It makes up approximately 68% of the total energy content of the universe. And we have essentially no idea what it is. The most natural explanation in physics is that it is a property of the vacuum, a kind of energy inherent in empty space, sometimes called the cosmological constant. Einstein actually proposed this idea and then abandoned it. Modern observations suggest he was right to propose it, but wrong to abandon it. But here is the problem. When physicists calculate what the vacuum energy should be from quantum field theory, they get a number that is roughly 10 to the power of 120 times too large. That is not a small discrepancy. It is, by some measures, the largest discrepancy between theory and observation in the history of science. Something is desperately wrong with our understanding of either quantum mechanics, or gravity, or the vacuum, or all three. Dark energy will determine the fate of the universe. If it remains constant, the universe will expand forever, growing colder and emptier until the last stars burn out. If it grows stronger over time, it could eventually tear apart galaxies, then solar systems, then planets, then molecules, then atoms themselves, in what cosmologists call the Big Rip. We don't know which will happen. We don't know what dark energy is. We only know it is there, pressing outward against everything, making the universe larger with every passing moment. There is a puzzle in physics that sounds like it should have a simple answer, but doesn't. The universe's physical laws appear to be precisely tuned for the existence of complexity in life. Consider gravity. If it was slightly stronger, by a factor of only a few percent. Stars would burn through their fuel too quickly, collapsing before planets could form around them, before life had time to develop. If gravity was slightly weaker, gas clouds would never collapse into stars at all. The universe would be dark and empty. Or consider electromagnetism. Change its strength by a small fraction. In the chemistry of carbon, the basis of all known life, becomes impossible. Atoms don't bind in the right ways. Molecules don't form. The remarkable flexibility of carbon chemistry that underlies every living thing vanishes. Or the strong nuclear force which holds atomic nuclei together. If it were slightly weaker, nuclei would fly apart. Atoms would not exist. No chemistry, no planets, no life. If slightly stronger, hydrogen would fuse too readily, and stars would burn out in seconds. These constants, gravity, electromagnetism, the nuclear forces, the mass of the electron, the cosmological constant, appear balanced with extraordinary precision. Change any of them by small amounts, and the universe becomes sterile. Why do they have the values they do? This is called the fine-tuning problem, and it has no agreed solution. 3 broad answers are proposed. The first is coincidence. The constants just happen to have these values, and we're here to notice it, because if they didn't, we wouldn't be. This is logically valid, but feels unsatisfying. The second is a multiverse. If countless universes exist with different constants, we necessarily live in one where life is possible. This elegantly sidesteps the fine-tuning, but requires the existence of universes we can never detect. The third is a deeper theory. Perhaps there are principles we haven't discovered yet that fix the constants at exactly these values, that make them not arbitrary at all, but necessary. None of these has been confirmed. The universe is set up for us with a precision that seems almost deliberate, and we don't know why. Let me tell you about the boundary of what we can ever see. Light travels at approximately 300,000 kilometers per second. This is not just the speed of light in some ordinary sense. It is a fundamental speed limit built into the structure of space-time. Nothing with mass can reach it. Nothing can exceed it. This means that what we can observe is limited by how far light has had time to travel since the universe began. The observable universe, the sphere of space from which light has had time to reach us in 13.8 billion years, is about 93 billion light years across. Beyond that horizon, space continues. The universe almost certainly extends far beyond what we can see. Some cosmological models suggest it is hundreds of times larger than the observable portion. Some suggest it is infinite. We genuinely don't know. But here is the strange part. The universe beyond our horizon is not just currently unreachable. It is permanently unreachable. Because the universe is expanding, and beyond a certain distance, galaxies are receding from us faster than light can travel from them to us. That light will never arrive. Those regions of space will never be in causal contact with us. There may be galaxies out there, stars, planets, perhaps life, that will never be able to communicate with us, not because of any practical barrier, but because the geometry of space-time puts them forever outside our reach. They exist in the same universe, but in a region we can never observe, never influence, and never receive information from. This is not a temporary situation awaiting better technology. It is the permanent shape of the universe. Most of reality is and will always remain hidden from us. And in that vast, unobservable expanse, almost anything might be happening. Let everything from tonight's first chapter settle. The question of why anything exists at all, which has no answer, and perhaps cannot have one. The Big Bang and the inflation that preceded our ability to see, hidden behind a horizon of time. The arrow of time that the laws of physics don't require, but our entire experience depends on. The dark matter and dark energy that make up 95% of everything, invisible and unexplained. The fine-tuning of constants that seem chosen for the existence of complexity. The permanent horizon beyond which most of the universe hides. All of it real, all of it confirmed by evidence and measurement and decades of careful observation. All of it genuinely, stubbornly, beautifully unknown, and its deepest level. What I want to offer you as this chapter rests is not an answer to any of these questions. It is the feeling of what they point toward. You are lying here, on a planet that formed from the remnants of dead stars, orbiting a star that is itself unremarkable among 200 billion stars, in a galaxy that is itself unremarkable among hundreds of billions of galaxies, in an observable universe that is itself probably a tiny fraction of everything that exists. You are made of the 5%, held inside the 95%, asking questions that reach from the inside of your skull to the edge of space-time and back. The fact that questions this large can be asked by something as small and temporary as a human being is not a reminder of how insignificant we are. It is perhaps the most significant thing about us. Let your breathing slow. Let the weight of your body settle into the ground that has been here patiently for 4.5 billion years. Let the darkness between the stars be what it is, mostly unknown, full of questions no one has answered yet, extraordinarily patient. You don't need to solve any of this tonight. You just need to rest inside it. And that, it turns out, is enough. There is a place in physics where the ordinary rules stop working, not because the universe becomes chaotic there, not because physics breaks down in the sense of failing, but because the questions you can ask about reality change character entirely. The comfortable certainties of the everyday world, that a thing is either here or there, that cause precedes effect, that something either exists or doesn't. These stop being reliable guides. At the smallest scales, particles exist in superpositions of states that collapse only when measured. Two objects separated by the width of the universe can be correlated in ways that no signal could explain. Black holes crush matter to a point where space and time themselves lose meaning. These are not thought experiments. They are confirmed, tested, experimentally verified features of the world you inhabit. You are built from matter that behaves this way. Every atom in your body, every proton and neutron and electron, every quantum of energy in every chemical bond holding your cells together. Each of these obeys rules so strange that the physicists who discovered them spent decades arguing about what those rules meant. Some of them never agreed. Tonight I want to take you to that edge. Not to make it frightening, it isn't, but because the edge of the known is one of the most beautiful places in existence. Because standing at the boundary of what is understood and looking out at what isn't is a particular kind of experience that, in the right mood, at the right hour, feels less like anxiety and more like standing at the rim of something vast and dark and full. Come with me. Start with the strangest confirmed fact in all of science. A single particle can be in two places at once. Not approximately, not as a figure of speech, not in some loose metaphorical sense. Literally, physically, measurably, a single quantum particle can exist in a superposition of states, in multiple conditions simultaneously, until the moment it is observed. Here is what this means in practice. Fire an electron at a barrier with two narrow slits cut into it, and the electron passes through both slits simultaneously, interfering with itself on the other side, producing a wave interference pattern on the detector screen behind the barrier. This is not what you would expect from a particle, which should go through one slit or the other. It is what you would expect from a wave, spreading through both openings at once. Now add a detector at one of the slits, a device that registers which slit the electron actually passes through. The interference pattern disappears. The electron starts behaving like a particle. It goes through one slit or the other. The wave behavior vanishes the moment you measure which path was taken. The act of observation changes what happens. This has been tested with electrons, with photons, with atoms, with molecules containing hundreds of atoms. The results are always the same. When not observed, quantum objects spread through space as probability waves, existing in superpositions of all possible states. When observed, they snap into definite positions and properties. The measurement collapses the superposition into a single outcome. Why? This is one of the deepest unsolved problems in physics. It's called the measurement problem, and despite decades of work and several competing interpretations, there is no consensus answer. One interpretation, the Copenhagen interpretation, developed by Bohr and Heisenberg in the 1920s, simply says that quantum mechanics describes probabilities, not realities. The wave function is a calculational tool, not a description of physical reality. When you measure, you get a result. Don't ask what was happening before the measurement. Another interpretation, the many worlds interpretation, proposed by Hugh Everett in 1957, says that the wave function never collapses. Every possible outcome actually occurs. But when a measurement happens, reality branches. In one branch, the electron went through the left slit. In another branch, it went through the right slit. Both branches are equally real. The universe is constantly splitting into an enormous number of parallel versions of itself.
A third approach involves hidden variables, the idea that quantum mechanics is incomplete, that particles have definite properties we simply can't access, and that the apparent randomness reflects our ignorance rather than genuine indeterminacy. Experiments over the past few decades have ruled out certain kinds of hidden variables, but the measurement problem itself remains open. What counts as an observation? Does a measuring device count, or does a conscious mind have to be involved? Is consciousness somehow implicated in the collapse of the wave function? Most physicists resist this idea, but it hasn't been definitively ruled out either. The universe, at its most fundamental level, appears to behave differently depending on whether it is being watched. And we don't know why. Now let me tell you about something even stranger. In 1935, Einstein collaborated with Boris Podolsky and Nathan Rosen on a paper intended to demonstrate that quantum mechanics was incomplete. Their argument was elegant. It involved what happens when two particles interact and then separate. When two particles interact in the right way, they become entangled. Their quantum states become linked. They are described not by two separate wave functions, but by a single joint wave function that encompasses both. Now separate them. Send one to a laboratory in Geneva and one to a laboratory in Tokyo. Measure the spin of the particle in Geneva. Find it spinning up. Instantly, the particle in Tokyo is determined to be spinning down, not because a signal passed between them, faster than any signal could travel, instantly, across any distance. Einstein called this spooky action at a distance. He argued it proved quantum mechanics was missing something, that there must be hidden variables, predetermined outcomes, something that explained the correlation without requiring instantaneous influence across space. He was wrong.
In the 1960s, physicist John Bell derived a mathematical test, now called Bell's theorem, that could distinguish between quantum mechanics and any hidden variable theory. In the 1980s and after, experiments confirmed that the correlations between entangled particles are stronger than any hidden variable theory allows. The particles are genuinely entangled. Measuring one instantly affects the other, regardless of distance. No information travels between them. You can't use entanglement to send a message, because the outcome of each measurement is random, but the correlations between the outcomes are non-local. They cannot be explained by anything that passed between the particles, at or below the speed of light. The universe is connected in ways that bypass space. Two particles, once entangled, remain connected across any distance, through any barrier, for any length of time, until one of them interacts with something else and the entanglement is broken. This is not a theoretical speculation. It is one of the most precisely tested phenomena in all of science. Quantum computers, quantum cryptography, quantum communication networks,
All of these are being built on the reality of entanglement. And yet, why entanglement exists, what it says about the deep structure of space and reality, whether it hints at a more fundamental level of reality, where space itself is not the basic ingredient. These questions remain open. Some physicists now suspect that entanglement is not a strange feature of quantum mechanics, but a clue to something deeper. That space itself might emerge from entanglement, that the geometric relationship between regions of space might be built from quantum correlations. In this picture, the spooky action at a distance wouldn't be mysterious, because distance itself would be a secondary concept, built from something more fundamental. But this is speculation, beautiful speculation, actively being explored, not yet confirmed.
For now, two particles, separated by any distance, correlated beyond what space should allow. The universe is stranger than it looks. Gravity is the force you know best. You have felt it every moment of your life. It holds you to the ground, keeps the moon in orbit, governs the motion of planets, shapes the large-scale structure of the cosmos. It was the first fundamental force to be mathematically described by Newton in the 17th century, and the description was so good it sent spacecraft to the moon. But gravity is deeply strange. Here is the first strange thing. Gravity is almost unimaginably weaker than the other fundamental forces. The electromagnetic force, the force that governs how atoms bind into molecules, how light propagates, how computers work, is roughly 10 to the power of 36 times stronger than gravity. That is a million, billion, 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 billion times stronger. You can feel this directly. Hold a small magnet near a paperclip. The magnet wins against the gravitational pull of the entire Earth. Why is gravity so weak? We don't know. This is called the hierarchy problem, and it is one of the major unsolved puzzles of particle physics. Some theories propose that gravity is actually strong, but spreads into hidden extra dimensions, diluting its apparent strength in our observable three-dimensional space. Others suggest it points to physics we haven't discovered yet. No explanation has been confirmed. The second strange thing about gravity is that it refuses to cooperate with quantum mechanics. General relativity, Einstein's theory of gravity, our best description of how mass curves spacetime, is extraordinarily accurate at large scales. It predicted the existence of black holes, the bending of light around massive objects, gravitational waves rippling through spacetime from colliding neutron stars. Every prediction has been confirmed. Quantum mechanics, our best description of how particles and forces behave at small scales, is extraordinarily accurate at small scales. It predicted the existence of the Higgs boson, the precise energy levels of atoms, the behavior of semiconductors. Every prediction has been confirmed. These are the two most successful theories in the history of science. They are mathematically incompatible. When you try to apply quantum mechanics to gravity, when you try to describe gravity as particles and fields and probability waves, the way all the other forces are described, the equations produce infinities. not large numbers, literal mathematical infinities, meaningless outputs that tell you the theory has broken down. Physicists have been trying to reconcile gravity and quantum mechanics for nearly a century. String theory attempts it by proposing that particles are not points, but tiny, vibrating strings of energy, with gravity emerging from the lowest mode of vibration. Loop quantum gravity attempts it by proposing that space-time itself is made of discrete quantum units, a fabric woven from finite loops of geometry. Neither has been confirmed by experiment. A complete theory of quantum gravity remains one of the great unsolved problems in physics. Without it, we cannot describe the interior of black holes, the first moments after the Big Bang, the ultimate fate of space-time itself. The two pillars of modern physics hold up the entire edifice, and they don't fit together. Now let's go somewhere that requires both theories simultaneously, and where both simultaneously fail. A black hole. Black holes form when a mass is compressed into a small enough volume that its gravitational pull becomes so strong that nothing, not matter, not light, not any signal or influence of any kind, can escape. The boundary of no return is called the event horizon. What lies inside is, in the strict physical sense, invisible to the universe outside. We know black holes exist. We have observed the orbits of stars around the supermassive black hole at the center of our galaxy. We have detected gravitational waves from colliding black holes. In 2019, the Event Horizon Telescope produced the first direct image of a black hole's shadow, a dark region surrounded by a glowing ring of heated gas at the center of the galaxy M87. What happens inside is another matter. According to general relativity, matter falling into a black hole is crushed toward the center into a singularity, a point of infinite density where the equations break down, where space-time curvature becomes infinite, where the laws of physics as we know them cease to apply. Most physicists believe that singularities are not real features of nature, but signs that our theory has reached its limits. A complete theory of quantum gravity, if we had one, would presumably describe what actually happens at the center of a black hole, replacing the singularity with something finite and physically meaningful. But we don't have that theory, so the center of every black hole in the universe is, for now, a place where our understanding ends. A location in real space where real things happen that we cannot describe. And there is a deeper puzzle still. In the 1970s, Stephen Hawking made a remarkable discovery. Black holes, he showed, are not completely black. Quantum mechanical effects near the event horizon cause black holes to emit radiation, a faint trickle of particles that carries energy away from the black hole, slowly over unimaginable timescales, causing it to lose mass and eventually evaporate entirely. This radiation, called Hawking radiation, has never been directly observed. Real black holes are surrounded by such violent and energetic environments
that the faint Hawking signal is completely swamped. Detecting it may be beyond the capability of any instrument we can conceive of building. But the theoretical prediction has enormous consequences. Because if black holes evaporate, then everything that fell into them, every particle, every atom, every piece of information about what they were, eventually disappears. And this violates a fundamental principle of quantum mechanics. In quantum mechanics, information is conserved. The quantum state of a system evolves in a way that is in principle reversible. You can always, in principle, run the equations backward and recover the initial state. Information is never destroyed. But if black holes evaporate completely and the Hawking radiation carries no information about what fell in, then the information is gone. Permanently, irrecoverably, destroyed. This is the black hole information paradox. It has been one of the central problems in theoretical physics for 50 years. Stephen Hawking himself initially argued that information is destroyed in black holes, that this was simply a fact about the universe we had to accept. Later, he changed his mind and proposed that information escapes, encoded in subtle correlations in the Hawking radiation. Others have proposed that information is stored on the event horizon itself, in a two-dimensional holographic encoding, or that black holes don't fully evaporate, but leave behind stable remnants carrying the information, or that the very framework of quantum mechanics needs to be revised. In 2019, a new approach using techniques from string theory suggested that information does escape, that the Hawking radiation is subtly correlated in ways that encode the information about what fell in. But the mechanism is not fully understood, and the calculation involves assumptions that not everyone accepts. The paradox is not resolved. Somewhere in every black hole, the information from everything that ever fell into it is doing something. We don't know what. And the answer, when it comes, will almost certainly require a revolution in our understanding of either quantum mechanics, or gravity, or space-time itself.
Let me take you somewhere quieter now, away from black holes and singularities, away from the violent edges of physics, to a question that is strange in a different way, more intimate, more puzzling in its simplicity. Why does mathematics describe the universe? Mathematics is a human invention. It begins with counting, with the abstract manipulation of symbols, with patterns and relationships that exist in the mind. It is created by human beings, often with no practical purpose in mind, often as pure intellectual play. And yet, the mathematics that physicists invent to describe the universe works with an accuracy that has no right to exist, works at scales and in conditions far beyond anything the original inventors imagined. James Clerk Maxwell wrote down equations describing electromagnetic fields in the 1860s. His equations predicted that electromagnetic waves should propagate through space at a particular speed. That speed turned out to be the speed of light, revealing that light itself is an electromagnetic wave. Maxwell's equations also predicted the existence of radio waves X-rays, microwaves, all of the electromagnetic spectrum, discovered and exploited over the following century. All of it hiding in equations he wrote down to describe the behavior of electric and magnetic fields. Einstein's general relativity, written down in 1915, predicted the existence of gravitational waves, ripples in space-time caused by accelerating masses. They were first directly detected in 2015, exactly a century later, by instruments of extraordinary precision that measured a distortion of space-time smaller than 1,000th of the diameter of a proton. The Higgs boson was predicted by mathematics in 1964. It was experimentally confirmed in 2012. Again and again, equations written down on paper turn out to describe physical reality with uncanny precision. The universe seems to be, in some deep sense, mathematical.
Or at least, the structures of mathematics and the structures of physical reality overlap in ways that seem far too extensive to be coincidental. Physicist Eugene Wigner called this the unreasonable effectiveness of mathematics. He meant it as a genuine puzzle, not a compliment. Why should the abstract patterns that human minds find interesting match the structure of physical reality? Why should the universe be comprehensible in mathematical terms at all? One answer is that the universe is literally mathematical, that it is made of mathematics, that physical reality and mathematical structure are the same thing at the deepest level. This is Max Tegmark's mathematical universe hypothesis, and it is either profound or obviously wrong, depending on who you ask. Another answer is that mathematics is a language evolved to describe patterns, and the universe is full of patterns, so of course they match. But this doesn't explain why the match is so precise, why equations written with no physical application in mind turn out to describe reality at scales their inventors never imagined. Another answer is that we only notice when mathematics works. When it doesn't, we discard it. So there's a selection bias. We remember the successes. But the successes are too numerous and too precise for this to feel satisfying. The universe speaks mathematics. We don't know why. One more thing before this chapter rests. At the very smallest scales, far smaller than atoms, far smaller than protons, far smaller than any particle we have ever detected, there may be a limit, the Planck length, approximately 1.6 times 10 to the power of -35 meters, 100 billion times smaller than a proton. At this scale, the quantum fluctuations of space-time itself become so violent that the smooth fabric of space we experience at larger scales dissolves into something else. Something our current theories cannot describe. A quantum foam of space-time, perhaps. A seething, uncertain, fluctuating something at the very bottom of physical reality. Below the Planck length, the concepts of distance and space may not apply. there may be no such thing as smaller, not because we lack instruments to measure it, but because the concept of spatial distance itself breaks down. If this is right, and most physicists suspect it is, then reality has a bottom, a finest grain, a pixelation to the fabric of existence that we have never seen and may never see directly. Everything you have ever experienced, every measurement ever made, every structure that has ever existed, all of it is built from something that operates at scales below our ability to probe, from a quantum geometry of space-time that our best theories only gesture toward. What is at the bottom? We don't know. But whatever it has been there since the first instant of the universe. It underlies every physical process that has ever occurred, and it will be there long after the last stars burn out. The floor of reality is hidden from us, and from that hidden floor, everything rises. Let everything settle now. The superposition, a particle in two places at once until observed, an experiment that has been confirmed thousands of times and never explained. The entanglement, two particles correlated across any distance, connected through something that bypasses space. The weakness of gravity, a force that rules the cosmos but is barely present at the quantum scale, weaker than the other forces by a factor that has no explanation. The incompatibility of relativity and quantum mechanics, our two most successful theories, both perfect, both irreconcilable. The black hole, a region of space where physics ends at the singularity and information may or may not survive. The information paradox, a conflict between quantum mechanics and gravity that has no resolution. Hawking radiation, predicted but never observed, with consequences that shake the foundations. The unreasonable effectiveness of mathematics, equations that describe reality with a precision that feels almost impossible. The Planck scale, the bottom of physical reality, below which space and time may not exist. All confirmed, all unresolved, all actively being worked on by the most careful minds our species has produced. And all of it here, tonight, in the same universe as the bed you're lying in. The edge of the known is not somewhere else. It is everywhere. Every atom in your body is operating according to rules that no one fully understands. Every quantum of light that has ever touched your eyes was a particle in superposition until it wasn't. Every heartbeat is a chemical process built on quantum mechanics that still raises questions no one has answered. You are made of mystery, living inside mystery, resting in it. Let your breathing slow to something that doesn't need to be managed. Let the strangeness of quantum reality settle into something peaceful, not a problem to be solved, but a quality of the world, the texture of what exists at scales below your perception. The particles that make you don't need you to understand them to do their work. They have been doing it perfectly since before the earth existed. Let them continue while you rest. Come back to Earth now. From the quantum foam at the bottom of space-time, from the event horizons of black holes, from the mathematics that describes a universe no one fully understands. Come back to something closer, something you can touch. Come back to the living world, to the particular miracle of a planet that, 4.5 billion years ago, was a ball of cooling rock and churning ocean and violent atmosphere. A place of lightning and volcanic vents and ultraviolet radiation and chemistry running wild in warm, shallow pools and cold, dark depths. A place with no life whatsoever.
And then, at some point, at some specific moment that we cannot identify, in some specific location that we cannot pinpoint, through some specific process that we cannot fully reconstruct, something changed. Chemistry became biology. A collection of molecules began to do something that no collection of molecules had ever done before on this planet. It began to copy itself, to take in energy from its environment, to maintain itself against the tendency of all things to dissolve into disorder. It became, in some minimal but real sense, alive. That moment, unremarkable in its physical surroundings, unobserved by any eye, recorded in no fossil, is one of the most consequential events in the history of the universe. Every living thing that has ever existed on this planet is a descendant of that first flicker of biology. Every cell in your body carries the inheritance of that moment, billions of years ago, when the distinction between chemistry and life was crossed for the first time. And we have no idea how it happened. The origin of life is sometimes called the hardest problem in science. Not because we lack hypotheses, there are many, but because the gap between the chemistry of the early Earth and the simplest living cell is so vast, so filled with necessary steps, each of which seems to require the others, that bridging it has defeated every attempt so far. Here is the scale of the problem. The simplest living organism we know of, a stripped-down parasitic bacterium called Mycoplasma genitalium, contains approximately 470 genes. Its genome encodes the instructions for roughly 400 different proteins. Its cell membrane is a precisely structured barrier that selectively allows molecules in and out. Its machinery for replicating DNA involves dozens of specialized proteins, each with a specific shape and function, each produced by reading other genes, each requiring the whole system to be in place to be produced at all. This is the simplest life we know. It did not appear fully formed. It evolved from something simpler, which evolved from something simpler still, which, at the base, was not alive at all, but was a collection of molecules that somehow began the process of self-replication and metabolism, from which everything followed. What was that collection of molecules? The most widely accepted current hypothesis involves RNA.
RNA is a molecule similar to DNA, but simpler and more versatile. In modern cells, RNA serves as an intermediary, copying instructions from DNA and carrying them to the protein-making machinery. But RNA has a property that DNA lacks. Under certain conditions, RNA molecules can act as enzymes. They can catalyze chemical reactions, including reactions that help copy RNA itself. This suggests the possibility of an RNA world, a period before DNA and proteins, when RNA molecules both stored information and catalyzed their own replication. In this picture, life began with RNA molecules that could copy themselves, that made errors in copying that produced variation, that were subject to natural selection for more efficient self-replication. The hypothesis is compelling, but it faces serious problems. RNA is a complex molecule. Producing it from scratch under conditions that plausibly existed on the early Earth has proven extraordinarily difficult. The basic building blocks, nucleotides, can be synthesized under certain conditions, as experiments beginning with the Urey-Miller experiment in 1952 have shown. But assembling nucleotides into functional RNA chains, under conditions where they don't immediately fall apart, remains an unsolved challenge. And even if RNA formed, where did it form? The question of where life began is as open as the question of how. Two environments have dominated the debate for decades. The first is hydrothermal vents on the ocean floor. These are cracks in the seafloor where superheated water, rich with minerals, pours out from volcanic activity below. They exist today, and they support thriving ecosystems that derive energy not from sunlight, but from the chemical energy of the vent fluids. In the 1970s, when deep-sea hydrothermal vents were first discovered, the realization that life could exist in such extreme environments, completely independent of sunlight, transformed thinking about where life might have originated. The chemistry of hydrothermal vents provides energy and mineral catalysts. Some vents produce alkaline water with a natural proton gradient across their mineral walls, a gradient remarkably similar to the gradient that modern cells use to generate energy. The biologist Nick Lane has argued that life may have originated in these alkaline vents, with the chemistry of the vent essentially doing the work that cells later learned to do for themselves. The second environment is shallow surface pools, the warm little ponds that Darwin speculated about in a famous letter in 1871. These pools, exposed to sunlight and atmosphere, would experience cycles of wetting and drying as water evaporated and returned. These cycles could concentrate and dry molecules, driving reactions that require energy. Chemist John Sutherland has shown that certain nucleotide building blocks can form under conditions that resemble these shallow pools. Both environments have advocates. Both have evidence in their favor. Both face challenges. And both may be right. Life may have required contributions from multiple environments, with molecules formed in one place being carried to another by rain or tidal action or simple flow. We don't know where life began. We don't know how it began. What we know is that it did begin, and that everything alive today, every bacterium and fungus and plant and animal and human being, every living thing that has ever drawn breath or captured sunlight or reproduced, is the downstream consequence of that single event. Here is a question that seems like it should have an obvious answer, but doesn't. Why DNA? All life on Earth uses the same molecule to store genetic information. The double helix, with its 4 base pairs arranged along 2 complementary strands, is universal. Every bacterium, every oak tree, every elephant, every human being reads the same genetic alphabet. The code by which sequences of bases are translated into sequences of amino acids, the genetic code, is virtually identical across all life. This universality suggests that DNA and the genetic code are not just one solution among many. They appear to be a solution that arose once, early in life's history, and was inherited by everything that followed. But why this solution? Why a double helix specifically? The structure is elegant. The 2 complementary strands provide a built-in template for replication, each strand serving as the pattern for a new copy. The double helix is chemically stable in ways that single-stranded molecules are not, protecting the information from chemical damage. Its bases can be packed densely enough to store enormous amounts of information. Your genome contains about 3 billion base pairs, encoding the instructions for every protein your body makes. But could other structures work? Could other molecules store genetic information as well or better? In principle, yes. Chemists have synthesized alternative genetic molecules, XNA they're called, for xenonucleic acids, that can store information and even evolve under laboratory conditions. Some of these molecules are more chemically stable than DNA. Some can fold into complex shapes that DNA cannot. So why DNA? Why these 4 bases and not others? One answer is contingency. DNA won the competition among early replicating molecules by chance, and once it was established and everything else was built around it, there was no going back. Evolution is conservative. A mutation that changes the fundamental architecture of the genetic system is overwhelmingly likely to be lethal. Another answer is that DNA is genuinely optimal, that something about its specific chemistry makes it the best available solution to the problem of storing and replicating large amounts of biological information. We don't know which answer is right. We don't know if life elsewhere in the universe, if it exists, uses DNA or something else entirely. We don't know if the universality of DNA on Earth reflects its optimality or its historical accident. Every living thing on Earth reads from the same book. We don't know why that book was written in that particular language. Let me tell you about something that is alive and not alive at the same time.
Viruses. A virus is a package of genetic information, DNA or RNA, enclosed in a protein coat. Some viruses have an additional lipid membrane. They range in size from about 20 nanometers to about 1,500 nanometers. The largest are just barely visible under a light microscope. They cannot reproduce on their own. They have no metabolism. They don't consume energy or produce waste. By most definitions, they are not alive. And yet, they evolve. They respond to selective pressure. They mutate and adapt. They have been shaping the evolution of life on Earth for as long as life has existed. There are more viruses on Earth than there are stars in the observable universe. And viral DNA makes up a significant fraction of the human genome. Where did they come from? 3 hypotheses compete. The first is that viruses are ancient, that they predate the cell, that they are survivors from the RNA world, stripped down replicating molecules that never made the leap to cellular life. The second is that viruses are escaped genes, pieces of genetic material that at some point broke free from cellular life and acquired the ability to move between cells. In this view, viruses are not ancestors of life, but runaways from it.
The third is that viruses are degenerate cells, organisms that were once fully cellular, but were stripped down over evolutionary time through parasitism until only the essential replication machinery remained. Evidence exists for all 3. Different viruses may have different origins. The question may not have a single answer. What is clear is that viruses have been with life for its entire history. They are woven into our genome. About 8% of human DNA is derived from ancient viral infections. They have driven the evolution of immune systems, of sex, of the placenta. Some researchers argue that the eukaryotic cell, the complex cell type that makes up all animals, plants and fungi, may itself have arisen from an ancient merger between a bacterium and a virus-like entity. Life and viruses are not separate phenomena. They have been entangled since the beginning, and how that entanglement began remains unknown. Here is something that will follow you into sleep if you let it. A Greenland shark was caught in the North Atlantic in 2016. Using radiocarbon dating of proteins in the shark's eye lens, proteins that form early in development and are never replaced. Researchers estimated its age, approximately 400 years old. This shark was alive before the 30 Years' War, before the founding of Harvard University, before Newton published his laws of motion. It had been swimming in the cold, dark waters of the North Atlantic since the early 17th century, moving slowly through the deep, eating and reproducing, and doing whatever Greenland sharks do. The 4 centuries, the oldest confirmed individual vertebrate ever recorded, and Greenland sharks may live even longer. The margin of error in the dating suggests some individuals could be pushing 500 years. The sharks reach sexual maturity at around 150 years old. They are the most of human recorded history, still adolescents. How? Greenland sharks live at temperatures close to freezing, which slows their metabolism to an extraordinary degree. Their hearts beat slowly, their movements are deliberate. They grow less than a centimeter per year. Everything about their biology operates at a pace that seems designed to extend life. But the mechanisms underlying their extraordinary longevity are not fully understood. Their DNA repair systems appear unusually efficient. Their antioxidant defenses seem robust. Their cells may be particularly resistant to the damage that accumulates in most animals over time. The Greenland shark is not alone in its defiance of expected aging. The ocean quahog clam, a species of hard-shelled clam found in the North Atlantic, can live for over 500 years. One individual, nicknamed Ming, was estimated at 507 years old when it was collected by researchers in 2006. The bowhead whale lives for over 200 years, swimming beneath Arctic ice with a body that resists cancer at rates that should be impossible for an animal of its size. Here is the puzzle the bowhead whale poses. Large animals have more cells than small ones. More cells means more cell divisions over a lifetime. More cell divisions means more opportunities for mutations to accumulate. More mutations means more cancer. By this logic, a whale should have an almost certain chance of developing cancer during its long life. Instead, bowhead whales show remarkably low cancer rates. This discrepancy is known as Peto's paradox, the observation that cancer rates don't scale with body size the way they should. Elephants have it too. So do whales. So do naked mole rats, those extraordinary small rodents that live 10 times longer than their size would predict and appear almost immune to cancer. In elephants, researchers have found extra copies of a tumor suppressor gene called TP53, a gene involved in detecting and eliminating cancerous cells. Humans have 2 copies. Elephants have 20. This may explain their cancer resistance. In naked mole rats, the mechanism appears to involve a particular sugar, hyaluronan, that forms a dense matrix around cells, preventing them from crowding together in ways that can trigger cancerous growth. In bowhead whales, the mechanisms are less clear. Perhaps their DNA repair systems are more efficient. Perhaps their immune surveillance of abnormal cells is more vigilant. Perhaps their metabolism generates fewer damaging byproducts. We don't know. What we know is that different species have found different solutions to the problem of aging. That aging is not a fixed law of biology, but a puzzle with multiple approaches. That the Greenland shark and the bowhead whale and the naked mole rat are living demonstrations that the biological clock can be set very differently from how ours is set. If we could read their solutions fully, medicine might be transformed. For now, they swim and burrow and live their long, strange lives, keeping their secrets. Now let me tell you about something smaller than any of these creatures, something almost impossibly small, a tardigrade. Tardigrades, commonly called water bears, are microscopic animals, typically between 0.1 and 1.5 millimeters long. They are found everywhere on Earth, in soil, in moss, in fresh water, in ocean sediments, on the slopes of the Himalayas, in the Antarctic. They have 8 stubby legs and a barrel-shaped body and a face that looks, under a microscope, remarkably like a friendly pig. They are, by almost any measure, indestructible. In a state called cryptobiosis, a tardigrade can survive conditions that would kill essentially any other animal. They can withstand temperatures from near absolute zero, minus 272 degrees Celsius, to over 150 degrees Celsius. They can survive pressures 6 times greater than the deepest ocean trench. They can endure radiation doses hundreds of times the lethal dose for humans. They can survive complete dehydration for decades, reviving when water is reintroduced. In 2007, tardigrades were sent into space aboard a European Space Agency mission. They were exposed to the vacuum of space, to cosmic radiation, to the full spectrum of solar ultraviolet radiation, without any protection. When they returned to Earth and were rehydrated, a significant fraction were alive. Tardigrades had survived open space. How? When conditions become extreme, tardigrades contract their bodies, retract their legs, and expel almost all water from their cells, replacing it with a sugar called trehalose that forms a glass-like matrix, protecting cellular structures from damage. Their metabolism drops to less than 0.01% of normal. They are not dead, but they are not, in any conventional sense, alive. They are in a state somewhere between. The proteins and molecular mechanisms underlying this extraordinary resilience are being studied actively. Tardigrades produce unusual proteins that appear to protect their DNA from radiation damage. Their ability to repair cellular damage when they revive is remarkable. But the full picture is not yet understood. A creature smaller than a period at the end of a sentence can survive conditions that would destroy almost anything else alive. The resilience of life, when you look at it carefully, is as mysterious as its origin. Let me take you now to one of the most breathtaking mysteries in all of biology. Every autumn, monarch butterflies leave their summer habitats across the United States and Canada and fly south. They are heading for a cluster of mountains in the state of Michoacán in central Mexico, to specific groves of oyamel fir trees, where they will overwinter in enormous congregations, covering every branch and trunk until the trees appear to be made of orange and black leaves. The journey is approximately 4,000 kilometers. The butterflies that make this journey have never made it before. They are the great-grandchildren of the butterflies that made it last year. The generations that lived during summer, breeding on milkweed plants across North America, never knew their great-grandparents, never received any teaching, never had any opportunity to learn the route, and yet they find it every year. The same groves, the same trees,
Sometimes researchers report the same individual trees their ancestors used. How does a butterfly that weighs less than half a gram, with a brain roughly the size of a pinhead, navigate 4,000 kilometers to a place it has never been, guided by information it never learned from any individual who knew it? Part of the answer involves the sun. Monarchs have a time-compensated sun compass. They use the position of the sun as a directional reference, adjusting for the time of day using an internal clock. Experiments in flight simulators have confirmed this. But on cloudy days, monarchs keep flying in the right direction. They appear to have a backup system that doesn't rely on sunlight, possibly a magnetic sense, an ability to detect Earth's magnetic field and use it for orientation. And even this doesn't fully explain the precision. Knowing to fly southwest doesn't tell you to stop at these specific mountains among the many mountain ranges of Mexico. Something more specific than a compass bearing is carrying these butterflies to a precise destination. How is this information encoded in the genome of an animal that has never seen the destination? How does evolution write a map? We don't know. The monarch migration is, when you hold it carefully, one of the most extraordinary phenomena in the living world. A navigation system of unknown mechanism, inherited across generations that never meet, precise enough to bring half a gram of butterfly to the same grove of trees, year after year. The living world contains navigational technologies that we have not yet learned to read. And now the deepest biological mystery of all. Why do we sleep? Every night you lose consciousness. Your awareness of the world around you fades. Your muscles relax. Your body temperature drops. Your brain enters a series of cycles through different states, each with its own characteristic electrical activity. For roughly 7 or 8 hours out of every 24, a third of your life, you're absent. This is a remarkable fact when you consider it from an evolutionary perspective. An unconscious animal is a vulnerable animal. It cannot flee predators. It cannot find food. It cannot respond to threats. The cost of sleep in evolutionary terms is enormous. And yet, every animal sleeps, or does something that appears to serve the same function. Dolphins sleep with one hemisphere of their brain at a time, alternating sides, so they never become completely unconscious. Migratory birds sleep in flight, taking microsleep episodes of a few seconds at a time. Some fish hover nearly motionless. Some insects show reduced responsiveness and activity during certain periods. The universality of sleep across the animal kingdom suggests it is not optional, that whatever sleep accomplishes is so important that evolution has maintained it, despite its costs across hundreds of millions of years of separate evolutionary history. But what does it accomplish? There are several theories, each supported by evidence, none complete. Sleep appears to consolidate memory. Experiments consistently show that sleeping after learning something improves retention. The brain, during certain stages of sleep, appears to replay the day's experiences, reactivating the neural patterns associated with new memories. strengthening the synaptic connections that encode them. People who sleep after learning perform better on tests the next day than those who stay awake. Sleep appears to clear metabolic waste from the brain. The lymphatic system, a network of channels around blood vessels in the brain, appears to be far more active during sleep than waking. Cerebrospinal fluid flows through these channels, washing away proteins and metabolic byproducts that accumulate during waking activity. Among the proteins cleared this way is amyloid beta, the protein associated with Alzheimer's disease. Chronic sleep deprivation leads to amyloid accumulation. Sleep appears to regulate the immune system. People who sleep less than 6 hours per night are significantly more susceptible to infection. Sleep deprivation impairs immune function in ways that are measurable and significant. Sleep appears to regulate metabolism, hormone production, cardiovascular function, and emotional regulation. The list of systems that sleep influences is so long that it begins to sound like sleep does everything, which may be the point. Sleep may be a master regulatory state that allows all of these systems to reset and recalibrate in ways they cannot while the organism is awake. But no single unifying theory explains why sleep has to involve unconsciousness. Why can't the brain perform its maintenance functions while the organism remains aware? Why does consolidating memories require the loss of consciousness? Why does clearing amyloid require turning off awareness? We don't know. We spend a third of our lives in a state whose purpose we have not fully understood. The most ordinary thing you do, the thing you are preparing to do right now, remains scientifically mysterious. One more thing. Your body replaces most of its cells over time. Your red blood cells live for about 4 months. Your gut lining replaces itself every few days. Your skin cells turn over every few weeks. Even neurons, long thought to be permanent, undergo some replacement in certain regions. Over the course of your lifetime, the atoms that make up your body are almost completely replaced multiple times. The carbon, the oxygen, the hydrogen, the nitrogen, they cycle through you and into the world and back again. The atoms in your left hand right now were almost certainly not there 10 years ago, and yet you persist. The experience of being you continues. Your memories, your character, your sense of yourself, these things endure through the constant physical replacement. This is the ship of Theseus, wearing biological clothes, the ship whose every plank was replaced remaining, or not remaining, the same ship. But here is what the biological version adds, that the philosophical puzzle doesn't. The replacement is not random, it is organized. The atoms that enter your body are directed to the right places by processes of extraordinary complexity, by proteins reading genetic instructions, by signaling molecules coordinating activity across trillions of cells, by systems of feedback and regulation that have been refined over billions of years of evolution. You are not a static thing. You are a process, a pattern that maintains itself by constantly replacing its physical substrate. And the process, the pattern, the organization, the persistent structure that is you, emerged from chemistry, from molecules that had no awareness, no intention, no knowledge of what they were building, that assembled themselves over billions of years of evolution into something that lies here tonight and wonders where it came from. Let everything settle now. The first living molecule, somewhere in the early earth, in a warm pool or a dark vent, or a place we haven't imagined, crossing the line from chemistry to biology in a moment no one observed, and no fossil records. The universality of DNA, a language chosen by all life for reasons we don't fully understand. The viruses that blur the line between living and non-living, woven into our genome. The Greenland shark, moving slowly through dark Arctic water for 4 centuries. The bowhead whale, resisting cancer with mechanisms that could transform medicine if we could read them. The tardigrade, surviving open space in its glass-like suspended animation. The monarch butterfly, navigating 4,000 kilometers to trees its great-grandparents knew. The sleep you are preparing to enter, necessary, universal, and not fully explained. All of it alive, all of it mysterious, all of it here on this particular planet that was once entirely lifeless. There is a thread running through all of these mysteries. Life is more ingenious than our understanding of it. Every time we look carefully at a living thing, at how it works, how long it lives, how it finds its way, how it survives, we find solutions to problems we didn't know had been solved. Tricks and mechanisms and strategies, refined over millions of years, that we are only beginning to read. The living world is not a solved problem, wearing a solved face. It is a deep and ongoing mystery, wearing the face of the ordinary. The grass, the moth, the slow shark in the dark water. You. All of them built from chemistry that became something else. All of them still, at the deepest level, unexplained. Let your breathing slow now to something unhurried. Let your body do what it knows how to do. The breathing, the circulation, the slow maintenance of all the systems that keep you alive, without any attention from you. It has been doing this since before you were conscious. It will continue long after you fall asleep. You are a process that maintains itself, a pattern that persists through constant change, a collection of mysteries, resting inside a larger collection of mysteries, on a planet that crossed from lifeless to living in a moment no one recorded. Rest now. The living world continues around you and inside you, doing its extraordinary work, asking no explanations. Let it. Everything we have explored tonight has been out there. The origin of the universe, the nature of dark matter, the quantum strangeness of particles, the hearts of black holes, the first living molecule, the ancient shark in the dark water, all of it outside, all of it in the world beyond the boundary of your skin. Now we turn around.
We go inward to the place that is simultaneously the most familiar territory you have ever inhabited and the least understood thing in the known universe, your mind. The awareness that is reading these words right now, the memory that connects this moment to all the moments before it, the dreams that are waiting for you just past the edge of sleep, the emotions that color every experience without being asked to, the creativity that produces ideas from silence, the love that shapes entire lives, the tears that fall for reasons that have no clean explanation. All of this happens inside a 3-pound organ made of approximately 86 billion neurons, each connected to thousands of others through synapses that fire in electrochemical pulses, producing patterns of activity that are in some way, in a way that no one has yet explained. You. The hard problem of consciousness is not a problem only for philosophers. It is a problem for anyone who has ever wondered, in a quiet moment, what exactly is happening when they notice that they are noticing something. Tonight we go there, gently, without needing to arrive anywhere. Begin with the fact that you are aware. Right now, in this moment, there is something it is like to be you. There is an inside, a perspective, the particular quality of this hour, the darkness, the weight of your body, the texture of the thoughts moving through you. These are not just physical events happening in the dark. They are experienced. They appear to you. They have a quality that is yours and no one else's. This seems so obvious, it barely seems worth saying.
And yet it is, when you look at it directly, one of the most extraordinary and completely unexplained facts about the universe. Here is a problem. We can describe in extraordinary detail what happens in the brain when you see a red apple. Light hits your retina, photoreceptors convert it to electrical signals. Those signals travel along the optic nerve to the visual cortex. Neurons fire in specific patterns that encode information about wavelength, shape, contrast, location. Higher brain areas integrate this information with memory and context. The brain identifies the object as an apple, and its color is red. This is a complete description of the neural process, and nowhere in it is there any mention of the redness of red. The actual experience of seeing red, the specific quality of that particular color, the way red looks, what philosophers call the quale of redness, does not appear anywhere in the description of the neural process. It is not in the firing of neurons. It is not in the electrical signals. It is not in the patterns of activity that encode the wavelength. And yet there it is, the redness, present and vivid and unmistakable. This gap between the physical description of what the brain does and the experiential reality of what you undergo is what philosopher David Chalmers called the hard problem of consciousness. All the other problems of consciousness, how the brain integrates information, how it directs attention, how it distinguishes waking from sleeping, these are hard in the ordinary sense. They are complicated but tractable. They will eventually yield to the usual methods of neuroscience. The hard problem doesn't yield. It is not a gap in our knowledge that more experiments will close. It is a conceptual gap, a gap between two different kinds of description, the physical and the experiential, that seems to resist bridging by any method we currently possess. Some philosophers argue the gap is illusory, that when we understand the brain well enough, the experience will be explained along with the mechanism. Others argue that consciousness is fundamental, that it is not produced by the brain, but is a basic feature of reality, as fundamental as mass or charge. Still others argue that our concepts are simply inadequate, that the question is confused, that we need a new way of thinking that doesn't yet exist. The neuroscientist Christoph Koch spent decades searching for the neurocorrelates of consciousness, the specific patterns of brain activity that correspond to conscious experience. He found correlates. He found that certain patterns of neural activity are reliably present when certain experiences occur. But finding correlates is not finding an explanation. Knowing which neurons fire when you see red does not explain why those firing neurons produce the experience of seeing red rather than no experience at all. You are experiencing something right now. No one knows why. Now let me tell you about memory. Your life is stored somewhere in your brain. Your first day of school, your earliest memory of a particular smell, the face of someone you loved, the feeling of a specific summer afternoon years ago. All of it is encoded in the patterns of synaptic connections between neurons in a network of astonishing complexity distributed across multiple brain regions. Or at least, that is approximately true. The reality is stranger. Memory is not like a recording. It is not like files stored on a hard drive, retrievable intact and unchanged. Memory is reconstructive. Every time you recall a memory, your brain does not simply play back a stored recording. It rebuilds the memory from fragments, from the stored traces of the original experience, combined with everything you know now, everything you feel now, the context of the moment of recall. And in the rebuilding, the memory can change. This has been demonstrated experimentally in ways that are deeply unsettling. Psychologist Elizabeth Loftus spent decades studying how memories can be altered by suggestion, by misleading questions, by information introduced after the original experience. In famous experiments, she showed that people could be made to remember events that never happened, car accidents with different details than actually occurred, objects present in a scene that weren't there, entire childhood experiences that were entirely fabricated. False memories, in Loftus's research, feel exactly like true ones. They are reported with equal confidence, equal emotional detail, equal certainty. The person remembering does not experience them as reconstructions. They experience them as recollections. This means that your confidence in a memory is not a reliable guide to its accuracy. The memories you are most certain about may have been subtly reshaped over the years of remembering. Each recall is a reconstruction. Each reconstruction is an opportunity for alteration. The memory you hold right now of some significant event in your life may be a palimpsest, a version built on a version, built on a version, each one slightly changed from the one before. And yet memory is the substance of identity. You are, in large part, the accumulation of what you remember. Your sense of who you are, your understanding of your own history, your relationships with other people, all of it depends on memory that is not a recording, but a living, mutable, reconstructing process. Why do some memories last a lifetime, while others fade in days? We don't fully know. Sleep appears to play a role. The brain during sleep replays experiences, consolidating some into long-term storage, while allowing others to fade. Emotion plays a role. Emotionally significant events are typically remembered better than neutral ones, though emotion can also distort. Repetition plays a role. Attention at the time of encoding plays a role. But the full picture of how a moment becomes a memory, how a memory persists across decades, and how it is retrieved from the vast network of the brain when you need it, this remains incompletely understood. One of the most haunting neuroscientific findings involves a patient known only by his initials, HM. Henry Molaison had surgery in 1953 to treat severe epilepsy. The surgeon removed most of his hippocampus, a seahorse-shaped structure deep in the brain that was the source of his seizures. The seizures improved dramatically, and HM could no longer form new long-term memories. He could remember his life before the surgery. His personality was intact. His intelligence was unaffected. He could learn new motor skills. He got better at tracing a star shape reflected in a mirror, improving with each session, even though he had no memory of the previous sessions. But every day he woke up, not knowing what day it was. He did not recognize the researchers who had worked with him for years. He could not remember conversations that had taken place an hour before. Each moment existed for him, and then was gone, leaving no trace in his conscious memory. HM lived like this for 55 years. He died in 2008. He contributed more to our understanding of memory than perhaps any other individual in the history of neuroscience. What his case revealed is that memory is not a single thing. It is a collection of different systems, each handling different kinds of information, each dependent on different brain regions. The hippocampus is critical for the formation of new, episodic memories, memories of specific events and experiences. But procedural memory, how to do things, how to perform skills, appears to be stored elsewhere. HM could learn, he just couldn't remember learning. The machinery of memory is distributed, specialized, and still only partially mapped. Your life is in there somewhere, reassembled fresh each time you remember it. Let me tell you something about the brain that will stay with you. It generates its own light, not metaphorically, not as a figure of speech, literally. The neurons in your brain produce a faint bioluminescence, a glow so faint it cannot be seen by any conventional instrument, but can be detected by extraordinarily sensitive cameras. This light is not thought to serve any function. It is a byproduct of the chemical reactions of metabolism, an incidental glow from the biological machinery running in the dark of your skull. But here is what is more interesting. In the transition towards sleep, in the hypnagogic state that lies between waking and dreaming, your visual cortex, freed from the business of processing external light, begins to generate its own patterns. Spontaneous neural activity produces the experience of brightness, of geometric forms, of colors, phosphenes, flashes of light that appear without any external light source, patterns, grids and spirals and moving forms, faces, landscapes. The brain, left to its own devices, in the absence of the world, begins to generate its own version of seeing. This is the entrance to dreaming, and dreams are themselves one of the strangest mysteries of the mind. Every night you enter a state of consciousness that is like nothing else in your waking experience. You lose awareness of your body. You lose awareness of your location in space and time. And your brain constructs a world, not a vague impression of a world, a vivid, detailed, emotionally real world, populated with people and places and events, governed by its own internal logic, experienced as completely real in the moment of its occurrence. You do this every night, and we don't know why. We know a great deal about when dreaming occurs. The most vivid dreams happen during REM sleep, rapid eye movement sleep, named for the characteristic flickering of the eyes beneath closed lids during this stage. During REM, the brain shows a pattern of activity that in some ways resembles waking. Widespread activation, particularly in the limbic system, the emotional centers. At the same time, the brainstem sends signals that paralyze the body's muscles, preventing you from acting out your dreams. The evolutionary logic of this paralysis is clear enough. Without it, the dreaming person would thrash and move with the dream, disturbing sleep and potentially injuring themselves. But the evolutionary logic of the dreams themselves is not clear. One theory proposes that dreams serve memory consolidation. During REM sleep, the brain replays and integrates the experiences of the day, strengthening memories and making connections between new information and existing knowledge. The vivid narrative quality of dreams, in this view, is a byproduct of the memory processing machinery. Another theory proposes that dreams simulate threatening situations, that REM sleep is a kind of threat rehearsal, allowing the brain to practice responses to danger in a safe context. This would explain why anxiety dreams and nightmares are so common, why dreams so often involve pursuit and conflict and social threat. A third theory proposes that dreams are essentially random, that the sleeping brain generates activity and the narrative constructing machinery of the cortex interprets this activity as story, building coherent seeming scenes from neural noise. On this view, the meaning of dreams is the meaning imposed by the sleeping mind, not any meaning encoded in the dreams themselves. None of these theories is fully satisfying. None explains why dreams are so emotionally intense. None explains the phenomenon of lucid dreaming, in which the dreamer becomes aware that they are dreaming and can sometimes influence the dream's content. None explains why certain recurring dreams appear across cultures. The dream of falling, the dream of flying, the dream of being unprepared for an examination. Every night your brain constructs a world. You inhabit it completely, and then you wake up and it's gone. Where did it go? Where do dreams go when you wake? They don't go anywhere. They were never anywhere. They were patterns of neural activity, now dissolved back into the resting state of the sleeping brain. But while they were happening, they were as real as anything you have ever experienced. What is the difference in the end between the dream world and the waking one? Both are constructed by the brain. Both are experienced from the inside. Both feel real in the moment of their occurrence. The difference perhaps is consistency. The waking world is shared. It persists. It follows reliable rules. The dream world is private and temporary and follows rules only loosely. But the experience itself, the vividness, the realness, the sense of being somewhere, the brain produces this equally in both states. You have spent years of your life in worlds that don't exist, and when you were in them, you didn't know. Here is something about emotions that took science a long time to recognize. They are not interruptions of rational thought. They are not noise in the system, interference with the clean operations of reason. They are not primitive remnants of a more animal past that the higher brain struggles to overcome. They are information. Neurologist Antonio Damasio spent years studying patients with damage to specific regions of the prefrontal cortex, brain areas involved in emotional processing. These patients, after their injuries, appeared in many respects normal. Their intelligence was unaffected. They could reason, plan, remember. They were calm and articulate, but they could not make decisions. When faced with choices, even simple everyday choices, they would deliberate endlessly, generating pros and cons, weighing options, and never arriving at a conclusion. Some of them made catastrophically bad decisions in their personal and professional lives, over and over, unable to learn from experience. What was missing? Emotion, the gut feeling that typically accompanies decision-making, the sense that one option feels right and another wrong, the somatic marker that the body generates to guide choice. All of this was absent. Without emotion, pure reason turns out to be almost useless for practical decision-making. The emotional signal is not an interruption of the rational process. It is an essential component of it. We still don't fully understand where emotions come from. The brain structures involved are reasonably well mapped. The amygdala for fear and threat detection, the insula for disgust and interoception, the anterior cingulate cortex for conflict and pain, the nucleus accumbens for reward. But mapping the structures is not the same as understanding the experience. Why does loss feel the way it feels? Why does music produce a physical sensation of chills? The phenomenon called frisson, in some people and not others. Why does the sight of someone else's pain activate regions of your brain involved in your own pain experience, producing something that functions like vicarious suffering? The social emotions are particularly mysterious. Guilt, shame, pride, embarrassment. These are emotions that require awareness of other minds, awareness that you are being seen, judged, compared. They are emotions that only make sense in the social context. Why should the brain produce experiences tied to the imagined perspectives of others? Because we are, fundamentally, social animals. Because the emotional lives of our ancestors were shaped by evolution in groups, where the perceptions of others were critical to survival and reproduction. Because a brain that evolved to navigate complex social environments built into its emotional repertoire the experiences that guide social behavior. But this evolutionary story, compelling as it is, doesn't explain the experience. It doesn't explain why shame feels the way it feels, why love is experienced as it is, why grief has a particular quality it has, the weight of it, the way it settles into the body, the way it ambushes you weeks later when you encounter something the lost person would have noticed. Emotions are the coloring of experience, and the mystery of why physical processes in the brain produces particular coloring, rich, varied, sometimes devastating, sometimes transcendent, is the mystery of consciousness wearing different faces. Let me tell you about something called the default mode network. When you are not actively engaged in a task, when you're not solving a problem or reading or having a conversation, your brain does not go quiet. It shifts into a particular pattern of activity involving regions of the medial prefrontal cortex, the posterior cingulate cortex, the angular gyrus, and others. This network is active when you are mind-wandering, when you are thinking about the past or imagining the future, when you are thinking about other people, their beliefs, their feelings, their perspectives, when you are constructing narratives about yourself and your life. The default mode network is, in some sense, the network of the self. It is active when the brain is doing what it does when left to its own devices, not processing the external world, but processing the internal one, replaying experiences, anticipating futures, modeling of the minds, constructing the ongoing narrative of who you are. What is remarkable is how much of your brain's total energy is consumed by this network. The brain uses roughly 20% of the body's total energy, despite being only about 2% of body weight. And the default mode network consumes allosteres, including leucine, enkephalin, and endorphin, and prolactin, a hormone involved in stress response. He proposed that crying removes stress-related biochemicals from the body, providing physiological relief. But these hypotheses are incomplete. They don't explain why the same phenomenon, tears, occurs in response to both grief and joy, both loss and reunion, both pain and transcendence. Why should the body use the same signal, the states as different as watching a child graduate and attending a funeral? Perhaps because what these states share is not their emotional valence, but their intensity, their significance, the sense of something mattering deeply. Tears may be the body's response to the recognition of what matters, which would make them, in a strange way, one of the most honest things we do, and why humans alone evolved this response. Why no other species sheds tears for emotional reasons remains unknown. You have in your life cried for things that mattered to you, and in doing so, you have participated in something that no other creature does, something mysterious and specifically human, something science has not yet fully explained. Let everything from this final chapter settle. The hard problem of consciousness, the gap between the firing of neurons and the experience of redness, between the physical and the felt, that no current theory bridges, the reconstructive nature of memory, not a recording but a living process, rebuilt each time it is recalled, capable of change and error and beautiful distortion. The brain's own light, the bioluminescent glow of metabolism in the dark of the skull, and the self-generated imagery of the hypnagogic state. Dreams, worlds constructed every night from neural activity, experienced as completely real, dissolved back into the brain on waking. Emotions as information, not interruptions of reason, but essential components of it, guiding decision and relationship, and the construction of a life. The default mode network, the self-referential machinery of the mind, active in apparent rest, consuming enormous energy, running the narrative of who you are. Tears, specific to humans, triggered by what matters, chemically distinct, evolutionarily unexplained. All of it you, all of it mysterious, all of it happening right now, in the 3 pounds of tissue inside your skull, without any help from the conscious part of you that has been following these words. Here we are, at the end of a long journey through the unknown. We began in the darkness between the stars, in the 95% of the universe that is invisible and unexplained. We move through the quantum world, where particles exist in superposition until observed, where entanglement connects objects across any distance, where the mathematics of our 2 best series breaks down at the places that matter most. We came back to Earth and the mystery of life, how chemistry became biology in a moment no fossil records, how a Greenland shark persists for 4 centuries, how a monarch butterfly finds trees its great-grandparents knew. And we ended here, in the interior, in the hard problem of consciousness, the reconstructive nature of memory, the nightly mystery of dreams. 100 mysteries woven into 4 journeys, none of them solved, all of them real. What I want to offer you at the end of all of this is not a summary, not a conclusion, not a lesson, just a feeling, the feeling of being inside something vast and still mostly unknown, the feeling of being a temporary pattern of matter and energy, aware of itself, aware of its own mystery, resting for a few hours inside the larger mystery of a universe that has been going on for 14 billion years without needing anything from you. This is not a frightening feeling held correctly. It is one of the most spacious feelings available. Because when you feel genuinely small inside something genuinely large, when the questions are truly bigger than any possible answers tonight, the small urgencies of daily life lose some of their grip. The things that felt pressing become, for a moment, proportionate, held inside 14 billion years and 95% invisible universe. Most of what worried you today looks appropriately small. Not unimportant, just small. And in that smallness there is relief. Science is not a book of final answers. It is an ongoing conversation with the unknown. A conversation that has been going on for centuries and will go on for centuries more. Each generation inheriting the questions their predecessors couldn't answer and adding new ones of their own. Some of the mysteries we explored tonight will be solved in your lifetime. The origin of fast radio bursts may be confirmed. The nature of dark matter may be revealed by a particle detector that hasn't been built yet. The mechanism of monarch butterfly navigation may be fully mapped. The neural correlates of consciousness may be identified with new precision. Others will remain open for generations. The hard problem of consciousness may require entirely new conceptual frameworks that don't yet exist. The question of why there is something rather than nothing may resist every approach science can take toward it, and some may never be solved. Not because we lack intelligence, but because the questions reach beyond what any instrument or theory built inside the universe can access about the universe. The mystery of the first moment, the experience of redness, why the constants have the values they do, what it is like to be a Greenland shark in the dark, cold water. These may be permanently closed to us, and that is all right, because the questions themselves are valuable. The act of asking is valuable. The posture of genuine curiosity, of looking at the ordinary and seeing through it to the extraordinary hidden beneath. This is one of the best things a mind can do. You have a mind that does this, that has been doing it tonight, that will perhaps do it in the strange narratives of your dreams before morning comes. If you have been here all the way to this moment, if you traveled through black holes and quantum particles and ancient sharks and the hard problem of consciousness, and arrived here still listening, then something in tonight was for you. And if it was, I want to ask something small. Leave a like if you can. It is a small signal that reaches others, other minds lying awake in the dark, looking for something to carry them gently towards sleep. Something that treats their curiosity as a gift rather than a problem. Each light tells the world that slow and careful and genuinely wandering is something worth finding. And if soothing science has become part of your evenings, if these journeys into the strange and the beautiful have given you something to rest inside, subscribe if you haven't yet, so the next journey is waiting when you need it, so we can keep going to the edges together. This is a place for people who find wonder restful, who know that not knowing can be peaceful, who understand that the universe being larger and stranger than we can explain is not a problem to be solved, but a quality to be appreciated. If that is you, you have always belonged here. And now, there is nothing left to do. The quantum particles in your body are doing what quantum particles do, existing in superposition, entangled with the rest of the universe, following rules that no one fully understands. The neurons in your brain are preparing for the transition into sleep, slowing, shifting patterns, beginning the long inward work of the night. The default mode network is winding down its narrative. The memories of today are beginning their consolidation. Will continue moving long after tonight. Will continue moving long after tonight. Somewhere, monarch butterflies are gathered in their winter groves, covering the trees in living orange and black, waiting for the warmth that will send them north again, on a journey guided by something we cannot yet read. Somewhere, fast radio bursts are arriving at our instruments from galaxies billions of light years away, carrying information about their sources in signals we are still learning to interpret. The universe is doing what it does, without requiring anything from you. Let your breath slow to something that doesn't need to be managed. Let the weight of your body settle into wherever you are resting. Let the questions we've been carrying tonight become something soft, not problems requiring solutions, but companions for the journey into sleep. Interesting presences, good company in the dark. You are a conscious being on the living planet in an expanding universe. You spent this evening in the company of the questions that matter most. You don't need to answer any of them. You just need to rest inside the fact that they exist, that you exist, that there is something it is like to be you, here, now, at the end of this particular day, on the edge of sleep. That fact, unexplained, irreducible, extraordinary, is enough. It has always been enough. Good night. Sleep well. The mysteries will be here in the morning, and so will we.